Welcome to a series of lectures on environmental management. In this first lecture, we will get a bit of an introduction and then focus on conventional management using air pollution as an example. To begin this topic, I want to go back to the Sustainable Development Goals of the United Nations Development Programme, which provided the overarching framework for moving humanity towards a more sustainable future. These development goals embrace all three components of sustainability: environmental issues, social challenges, and economic considerations. Now, because the name of our program is REM, which stands for Resource and Environmental Management, I want to move our focus on the main environmental challenges again. And these are embodied in the goals 13, which is here, 14, and 15. The Sustainable Development Goal 13 is focused on climate action, which we'll discuss in more detail a bit later in the course. Sustainable Development Goal 14 aims to promote developments that conserve marine resources, and the goal of SDG, or Sustainable Development Goal number 15, is to promote a more sustainable use of the terrestrial ecosystems. To make these big overarching objectives more tangible, they are each divided up into several sub-goals that try to address more specific issues. What I'm showing you here on this slide are just a few of these sub-goals. So our success to fulfill the SDGs, or the Sustainable Development Goals, depends on our ability to solve each of these specific problems. Now, of course, each of these problems is unique and requires a tailored solution, but there are common themes for how these problems can be approached, and this is what I want to focus on in a series of these lectures. Now, how an environmental problem can be approached depends on two main characteristics of the problem. First, it depends on how well we understand the environmental system that we're dealing with. Is this thing just a simple system with just a few components, or is it a more complex system where we're not even sure if we know all of the components? We also want to ask, how well do we understand the different components, no matter how many there are of those components, and how do these different components interact with each other? The less we understand a system, the more uncertainty, and that's a key word that we want to focus on, is the uncertainty in the system that we have about whether our actions that we're planning will give us the desired outcomes. The second characteristic of the problem that determines how we should approach it is the severity of the consequences. How high are the stacks against us if we get this wrong? And how much time do we have to fix the issue? It is primarily going to be an inconvenience, and we can try, is it just going to sort of inconvenience us and we can try again? Or is the severity of this problem so big that the survival of our entire species is at risk? And could that risk be imminent? So these two characteristics are the guiding principles that we'll be focusing on in the three different approaches that we'll talk about for environmental management. We will talk about the conventional approach, the adaptive environmental management approach, and the precautionary principle approach. The conventional approach is used when we have a relatively good understanding of the problem and there is very low scientific uncertainty around the issue. In this case, we have the necessary background to implement very targeted interventions that go right to the heart of the issue. Adaptive management is used when we only have a limited understanding of the system and we are dealing with high scientific uncertainty. This is actually quite often the case because we're dealing with complex ecosystems that have many parts associated with them, and all of these multitude of parts are interacting in complex ways. However, adaptive management is only used in situations where, at least in the short term, consequences are relatively low, and there's time to learn from our actions and the potential adjustments that we make to our management process. Now, don't get me wrong, all of the environmental challenges we are dealing today are urgent and have the potential for severe consequences. So we're speaking in relative terms here when we talk about more or less or short or long-term consequences. The last management approach that we will be discussing is the precautionary approach, which is applied when we have high scientific uncertainty and the consequences of getting this wrong are very high and unacceptable to society. So let's illustrate each of these approaches with an example. We will be looking at urban air pollution for the conventional approach. We'll be looking at the Great Bear Rainforest as an example where adaptive management is being applied, and the protection of the stratospheric ozone layer for the application of the precautionary principle approach. So what I want you to take away from this series of lectures is a basic understanding of the three different management approaches. I want you to know under what circumstances the different approaches can be applied, and what steps are taken for that implementation, and what are the strengths and weaknesses in the different approaches. I would also like you to have a basic understanding of the environmental issues that I'm using to illustrate the different approaches. So you should be able to describe the sources of ground level ozone in the lower mainland, the objectives of the Great Bear Rainforest Agreement, and the role of stratospheric ozone layer. I also would like you to think about other possible examples for applications of the different management approaches. So let's get started with the topic of urban air pollution. Let's start our discussion on air pollution with two facts. First, we rely on clean air for living. Surprise, surprise. You gotta have clean air to breathe. If you think back to the lecture on market failures, you can probably figure out that clean air is a global common, which is defined as a non-excludable and depletable good. The second fact that we want to take into account is that more and more people are living in cities. The United Nations predicts that by 2030, which isn't very far away, 70% of the global population will be living in urban areas. And when you have lots of people in one place, all of their daily activities together tend to result in pollution that affects a lot of people. And this is why one of the sustainable development goals, the SDGs, is specifically targeted at cities. Now, the issue of urban air pollution emerged with the Industrial Revolution because burning coal became the primary energy source, and the resulting emissions were simply dumped into the atmosphere. You can really think of air pollution as a negative externality of industrial activity. In the early days, air pollution primarily consisted of sulfur dioxide and soot particles from the burning of sulfurous coal. Most of the time, winds would simply blow the pollutants away, but when conditions were just right, you could end up with really bad air quality. The pictures on this slide were taken in London during a particularly bad air pollution episode in 1952. It was a cold period in December with absolutely no wind when all the pollutants from the local industry got trapped in the London area. During these conditions, you would naturally get fog, which would further trap the emissions. The term smog is actually a combination of the words smoke and fog. So this event, which lasted for 5 days, was one of the worst air pollution episodes that the United Kingdom ever experienced, and resulted in 4,000 to 12,000 premature deaths and approximately 100,000 people suffering from respiratory illness. Now, since then, we've cleaned things up a little bit. If burning coal, which actually is something we should get away from anyways, we avoid burning coal with significant amounts of sulfur. So even now, when there are places that burn coal, for instance, for power generation, they try to use coal that's low in sulfur. We also treat the emissions from the coal-fired plants before releasing them to the atmosphere, and we filter out the soot particles. So what's termed clean coal technology has reduced the issue of air pollution and acid rain, but remember, burning coal is still a bad idea due to the high CO2 emissions that affect climate change. But we're not focusing on climate change right now. Modern air pollution is something very different. What we call air pollution now in an urban setting has main components of ground level ozone and PM 2.5, which stands for particulate matter that are smaller than 2.5 micrometers. A micrometer is 1/1,000,000th of a meter. So these are super tiny particles that are dangerous for us because they get deep into our lungs where they can cause damage. Now, even though these particles are tiny, they do affect visibility, which is what you can see on this image. Los Angeles was famous for this type of bad air quality in the 1950s, but these days, cities like Beijing, Shanghai, and many other cities are often in the news about their bad air quality. I think the images that you see on this slide are showing a good and a bad day air quality in Beijing. So the top one is the bad air quality. Now, even though the air quality in Vancouver is generally much better than cities with millions of people, we do typically get a few days every summer where the concentration of ground level ozone and the PM 2.5s are higher than the Canadian air quality standard, and visibility is affected. What you see on this slide are two photographs taken from downtown Vancouver, looking towards the Second Narrows Bridge, and just SFU. You can just see the hill starting from Burnaby Mountain on the right-hand side leading up to SFU. Obviously, the one on the left is on a good day, and the photograph on the right was taken on a day when the air quality was not so good. Now, I need to point out that this type of air pollution is very different from the smoke of the forest fires that we see sometimes during the summer and certainly over the last few years. Air pollution caused by forest fires also involves tiny particulate matter, but their source is very different. So we're not going to be talking about air pollution from forest fires. Instead, we're just going to focus on the air pollution in the city, independent of forest fires. Fundamentally, we can distinguish between two types of ozone in the atmosphere. There is the good ozone in the stratosphere that protects us from harmful ultraviolet radiation from the sun. And there is the bad ozone in the bottom layers of the atmosphere, and this is the one that causes health problems. Ground level ozone is a so-called secondary pollutant because we don't actually emit it as humans. So humans in our activities, we don't actually emit this ground level ozone. Instead, the ground level ozone forms as a result of a chemical reaction with other emissions, and these other emissions, which are called precursors. In the case of ozone, the precursors are nitrogen oxides, which is abbreviated as NOx, and volatile organic compounds, or VOCs. So these NOx, NOxs, and these VOCs react together in the presence of sunlight to produce ground level ozone. The ideal condition for the formation of ozone are late afternoons on hot, sunny summer days, which is when we often see this kind of pollution in Vancouver. Now, we've got precursor gases, NOx and VOCs, that interact with the ground level ozone. So where do these precursor gases, the NOx and the VOCs, come from in the Vancouver area? What you see on this slide are the largest emitters of these gases, published in a 2014 ground level ozone fact sheet from the Metro Vancouver. Nitrogen oxides are a byproduct of burning fossil fuels, which is clearly reflected in these numbers. The biggest emitters are dirty, rotten, regular old cars that we drive around, which account for approximately a quarter of all the nitrogen oxide emissions. Other sources of nitrogen oxides, the NOxes, include non-road engines, so engines that are running like lawnmowers and chainsaws, things that aren't on the road, generators, that sort of thing. Also ships out on the ocean, trucks, so the big long-haul trucks, furnaces of buildings, and railway engines. So anything that burns fossil fuels in Vancouver, well, anywhere, but we're talking about Vancouver, anything that burns fossil fuels is emitting or are emitting nitrogen oxides. The VOCs are organic chemicals, and they evaporate very easily at regular daytime temperatures. Here, the biggest contributor to the emissions in the Lower Mainland is the use of chemical products like solvents or paints. When you work with these types of products, there is always a very strong smell, which is the evaporated VOCs. If you look at house paint, for example, there's a real move, and they'll say on it low VOCs. And if you open up those paints, they don't have that really strong smell like a lot of the oil-based paints or the older paints did. But there are still lots of VOC, in this case paints, available. Now, the second most important group of emitters is natural sources, which is a bit unusual when thinking about pollution problem. So this means that the trees or other vegetations that naturally release VOCs, volatile organic compounds, contribute substantially to an air pollution problem in Vancouver. Of course, these natural VOC emissions are not the primary reason for the problem, but they do contribute to it. The rest of the sources are related to the use of gasoline, where you always have a little bit of evaporation, especially when you fill up your car. That's why you notice if you go to, certainly in California, I don't remember if it's in Washington State, but when you go to California and fill up the gasoline, there's a nozzle, there's a gasoline nozzle that you stick in the car, but there's an outside sleeve that's spring loaded and it pushes against your filler cap, and so, or the filler spout. And so when you put the gas filler into your car, it seals the gas tank so that those fumes are less likely to escape. I'm actually surprised we don't have them in Vancouver, but okay, maybe I'm not surprised. It's probably a matter of it costs too much money, or the gas stations think it costs too much money and the government hasn't mandated it. Anyways, that's what those are for down in California for sure. So so we've got this ground-based or ground-level ozone, and now we have these precursors, the NOx and the VOCs, floating around. So what are the effects of the ground-level ozone? Well, ozone is a very aggressive gas, and it's harmful for people even in relatively low concentrations. Particularly sensitive are children, seniors, and people with pre-existing respiratory conditions. Increased concentrations of ozone can cause simple irritations or coughing, like you get that feeling, the burning in the back of your throat. But they can also make existing lung and heart conditions even worse and can lead to premature deaths. The chart on the right shows the relationship between the concentration of ozone in the atmosphere and changes in mortality or hospital rates, death rates in hospitals. So the concentration on this graph is given in ppbs, which stands for parts per billion. So these are really tiny concentrations, parts of the concentration per billion parts of air. Now, I hope you remember that the concentration of CO2 in the atmosphere is currently around, okay, I'll pause there. What is the concentration of CO2 in the atmosphere? And it's somewhere above 415, 418, somewhere around there, depending on the day, parts per million. And that's parts per million, ppm. So we're talking now here with ozone of parts per billion. The blue line on this graph shows that at 40 parts per billion, again, a teeny tiny amount, the mortality in hospitals increases about 1%. And at 62 parts per billion, which is the Canadian standard that's allowed, or allowed to be considered normal, the increase is roughly 2%. This really highlights that there is no safe level of ground level ozone. And overall, it's in our best interest to reduce the levels of ozone as low as possible all the time. In addition to the effects on human health, ozone also negatively affects ecosystem and damages vegetation. Ozone reduces the growth of trees and reduces the yield of commercial crops. So think about that for a second. When all that pollution from Vancouver, all that ground level ozone and NOx and VOCs that we produce with all the cars in Vancouver, all of that gets pushed out into the Fraser Valley where all the agriculture is. So it reduces the yield for all those commercial crops. Ozone actually also damages building materials because it's actually a very corrosive gas. And on top of all this damage that it's doing, it's also a very powerful greenhouse gas. And so it adds to the problem of climate change. Now, this is what a typical ground level ozone episode in the lower Fraser Valley looks like. These numbers indicate the ozone concentrations at different locations throughout the valley. These episodes typically occur in the middle of the summer when we have a high pressure system with clear skies and only very light winds. This makes sure we have a lot of sunlight, and the precursors of the emissions from the cars and all the engines, they don't get diluted by strong winds, or they don't get washed out of the atmosphere by rains. So sunny, still days, those hot summer days. Also, the high temperatures from these hot summer days cause the vegetation to emit more VOCs. All of this together results in these elevated concentrations of ozones. Now, when you look at this map in detail, you might notice what I mentioned before, that we have the highest concentrations of ozone in Langley, Chilliwack, and Hope, which are out in the valley, actually far away from the main sources of the precursors emissions that are in the Vancouver area. And the reason for this is that these chemical reactions need some time to occur. And so all the precursors are in downtown Vancouver, but then there's light sea breezes that come off the ocean on these beautiful summer days. And what this does is it blows all the precursors up the Fraser Valley. And that's where the chemical reactions all take place. And therefore, the ozone levels are really high out there. So this is another example of a trans-regional negative externality, where people affected by the pollution live in a different region and do not necessarily benefit or gain from the activities that cause the pollution. So the people in the valley don't benefit from driving all the cars or using all the gas-powered engines in the Vancouver area. People in the valley are just living there, and they're not making any money by burning the gas down in the city. So that externality then moves up the valley. That's a negative externality, in this case, air pollution. Let's quickly summarize what we know about ground level ozone pollution. The health and environmental effects are well known. The science is very clear on how all of this works. And there are no truly safe levels of ozone for humans. Any level of ozone concentrations are bad for humans. The processes that form ozone are also well known, and the emissions of the precursor substances, the NOx and the VOCs, are linked to identifiable human activities. So we have a clear pathway from emissions to effects. This puts ground level ozone in a management category of environmental problems that are well understood and have relatively low scientific uncertainty. It's therefore well suited for the first management approach, which is the conventional management approach. So let's now look at what this looks like. The first step of the conventional management approach is to define a target that we want to achieve. We need to know what it is we're trying to achieve by our management approach. Now, based on what we know about the health effects of ground level ozone, we can set a maximum concentration that we are willing to accept as a society. We actually know that all levels of ground level ozone are bad, as we talked about earlier, but if we're going to accept that there's going to be some ozone out there because we're all not going to stop driving cars, then we want to set a maximum level beyond which we say, wait a minute, that's just too much ozone level. We're not willing as a society to accept that much risk. So in Canada, the air quality standards are defined under the Canadian Environmental Protection Act. Our current standard for ground level ozone specifies that the average concentration over an 8-hour period should remain below 62 parts per billion. Now, how exactly is this threshold calculated and interpreted? It's quite a bit more complicated. But for our discussion now, it doesn't really matter. What it just says is that we've set this, well, the Canadian Environmental Protection Agency has set this target. Now, in addition to specifying the standard, one also needs to set up a monitoring network so that you can actually measure whether you're currently at where you currently are and whether the efforts that you make are making a difference. The next step under this example of a conventional management approach to an environmental issue is to determine how much NOx, NOx, and how many VOC emissions are associated with different human activities. The table you see here is from the American Environmental Protection Agency, the EPA. The second column of the table shows the emissions of different compounds per mile driven, which are then multiplied by the average number of miles driven each year to calculate the annual emissions that are shown in the last column. So in 2008, the average car in the US drove 12,000 miles and on average emitted 27.4 pounds of VOC and 18.3 pounds of NOx every year. And then multiplying these amounts with the total number of cars in a given area gives us the total number of NOx and VOC emissions from cars. Now, this is just for cars, but we actually need to do this for every type of human activity that emits NOx and VOCs so that we get a good handle of the total amount of emissions. What you see in this chart are the NOx emissions in the Canadian part of the Lower Fraser Valley, divided up into different sources. This is what the different colors show, and also by geographic region. The wider column on the right are emissions from Metro Vancouver, which accounts for almost 90%, and the column on the left represent the emissions from the Fraser Valley Regional District. Now, we have two endpoints. We know how much precursors are currently being emitted, and we know the maximum concentration of ground level ozone that we're aiming for based on the Canadian EPA standards. So we have those two things in place. We know our target, and we know what the kind of output that we're seeing based on numbers of cars. The next step is to figure out what we need to do to hit our target or stay below the target. And this involves two steps. First, we figure how low do the precursor emissions need to be so that we get ozone concentrations below the target level. And to determine this, researchers use computer models that simulate both the chemistry and the meteorology in the region, so what the weather's doing. Similar to climate models, we can simulate different scenarios over and over again, super fast with computers, and then figure out what management works best based on our understanding of the system. Once we know how low the precursor emissions need to be, we need to figure out how we can achieve this reduction in the most economical way. It might be possible to solve the problem with a technical solution, like the catalytic converter shown on the slide, or we might have to create incentives so that people drive less. So these are a way of reducing the precursors at the source. We also need to compare the reduction potential, so how much reduction can we get from different sources to see where we can achieve the reduction most easily. So for instance, maybe it's easier and cheaper to fix the emissions of a few cargo ships, and that way it's easier than modifying every car in the Lower Mainland. But we don't know which one it is until you do the analysis. Once you know you can achieve your objectives, then you can actually create regulations and the mechanisms for enforcing those regulations. What you see in this table is the amount of NOx, NOxs, and particulate matter that a car was allowed to emit during the time that we had the Air Care program in British Columbia. Now, the Air Care program was a BC initiative that was started in 1992 to improve air quality, and it was done by systematically testing the emissions of all cars. So every year, whenever you had to get your car insurance renewed, you had to go to an Air Care station and get the emissions of your car tested. When the emissions of your car were below the standard, you were allowed to renew your insurance. But when you failed the test, so if the emissions were above the standard, you had to get your car fixed so that the engine wasn't producing so many emissions. You had to get that fixed before you were able to get your car insurance. So this ensured that cars that did not run properly got fixed, and older polluting cars would get taken off the road. After 22 years of service, the Air Care program was scrapped in 2014 because the government believed that the initiative was not effective anymore. Now, it was effective in getting where we wanted, but we didn't need to do it anymore because over that time, over those 2 decades, the technology in car engines had improved so much because the engines were starting to burn cleaner because of emission controls, particularly in California, which is the real market for cars and also has real stringent standards. So by meeting the California standards, it's easier for companies to meet the California standards because then they know they can sell their cars everywhere. But if they just met the standards for Texas, let's say, they wouldn't be able to sell their cars in California. So from the car manufacturer standpoint, what they end up doing is building all of their cars to meet the California standards. And so in BC, all the cars which met the California standards were also meeting the BC standards. And so the car technology for burning the fossil fuels improved so that there were not so many NOx and VOCs coming out of the tailpipe. So things like the catalytic converter, which absorb the gases. So because of all those improvements, the Air Care program could be scrapped. We didn't need to test every car anymore because all the cars, or the vast majority of them anyways, were passing. And what happens then is the program, the Air Care program itself, became too expensive to run for the marginal benefit that it provided. So it's a good news story in terms of things improving. Now, whenever you do an intervention like this, it's really key that there is monitoring that tracks progress. In the case of ground level ozone, you needed to monitor both the emissions of the precursor, so were there more or less emissions, and the concentrations of ozone in the atmosphere. So the chart on the left shows the NOx emissions in the lower Fraser Valley during the time of air care and projected into the future. Now you can clearly see that there was a significant drop in the overall emissions until about 2020, at which time they were predicted to level out until about 2030. During the same time period, there was also a reduction in the peak concentrations of ground level ozone and the number of days when the concentration was above the regulation threshold. So this showed how these two things were in sync. Let's summarize the steps of the conventional management approach that can be used for these relatively simple environmental challenges. So once you understand the ecological, environmental, and pollution system, once you understand the system that's causing the issue, you can set a target for an environmental parameter like the concentration of ground level ozone. Then you link this target parameter to specific human actions. So in this case, the emissions from cars. Then you create emission inventories of all the activities. In our example, we needed to figure out how much of the precursor gases got emitted every year. After that, you determine what reduction is required to reach your desired target and how to achieve that in the most economical way. Once you have a good plan for reaching your goal, you create the necessary regulations and infrastructure for enforcing them. And once that is underway, then you need to continuously monitor the conditions to ensure that your intervention is actually producing the desired results. Once you have reached the objective, then you can dismantle your system and you can move to the next environmental problem that requires attention. I hope this has given you a good overview of the conventional environmental management approach that's commonly applied when problems are relatively simple and well understood. We used urban air pollution to illustrate this approach, but there are many, many other examples. In the next lecture, we're going to move our discussion to the next type of management, which is the adaptive management approach. So that's the end of this lecture, and I thank you for listening.